watch it. I'm just going to record it. Okay, what we are looking at, again, will seem like we're going back to the first part of the semester, the idea of limits. And I say recall that we've got the limit as the input approaches negative infinity of the output values approaching an L, and as we approach negative infinity. This is the piece that's going to be different to us. In section, back in chapter 2, we were looking at limits that maybe the outputs went to infinity. Here, our outputs are going to be going, our inputs rather, are going to be going to infinity or negative infinity. And that's where that's how this is different. Now I say recall because you've had this information before. You've studied this in Algebra 2 and maybe Advanced Math. Will you talk about horizontal asymptotes? Just pause for a moment and let's think about that. What is a horizontal asymptote? How would you describe it? How would you see it? What would you expect to see on the graph if one had one? Okay, James, kind of enlighten us. What do you know about horizontal asymptotes?
I know horizontal asymptotes are asymptotes that goes this way.
Okay. Horizontally, yeah. Okay. So we'll draw that.
I forgot how to figure it out.
Okay. We're going to do that today. So we have this horizontal line, but what's so special? I mean, I dotted it. Why would we dot it? Why wouldn't I just draw a horizontal line there? Okay. Now we have to understand that there are some functions where it actually does cross the horizontal asymptote. But what we're talking about is that, and this is where this is important, as we go out to the utmost input values in both directions, we want to know what's happening. Now, here's a visual I want you to think about. We all know about zoom in and zoom out. We've seen that on lots of things. Google Map is a good one. If you zoom out far enough, you lose the detail. Okay? You lose the detail. When we zoom out, and when we zoom out, we're saying, let's take the input just as far as we can in this direction and in this direction. It's zooming out, and we lose the detail around here. And all we're really interested in when we do this, taking the inputs to the utmost, all we're interested in is if you were sitting on the moon, what would you see of the graph? And again, you wouldn't see the detail, you would see what we call the end behavior. So we're going to be talking about that idea, end behavior. Have you heard this before? We talk about end behavior asymptotes. Now we can talk about horizontal asymptotes as being horizontal lines. We actually have other asymptotes. They're not all horizontal. We can have a graph that in here can look like this, but when we zoom out, all we see is this. And so the end behavior would be the parabola. Inside, zooming in, we get a lot of detail. So in fact, we could maybe cross over the asymptote, the end behavior asymptote. Now horizontal is that, we are looking at a horizontal line. Okay, well let's go on. This is a kind of a bird's eye view. I guess that's an appropriate way of thinking of this, a bird's eye view of what's going on. Limits at infinity. If R is a positive rational number, rational, of course, it can be 1/2, 1/3, and so forth. And C is any real number. Then C divided by x to the R value is still 0. Now, as x goes to infinity, what I want to show you here is, I want you to think of this intuitively. We're going to get to the analytical work, but we have to feel this. We have to see it intuitively. Let me go down here and just put in an example. If I had f of x equals 4 divided by x to the, let's say 7th power. Okay? We don't need to know what that graph looks like. It's just, it's a function of some sort. But if I take x to approach infinity, so I'm going to let x go larger and larger and larger and larger. My question is, what are my output values doing? So let's think about this. If x is 1, what's the value of the output? 4. If x is 2, yeah, maybe we shouldn't use to the 7 because most of us don't know our 7s that well. Let's just say, well, let's just make it simple. We'll say x squared, okay? So it's still 4 if x is 1, okay? If x is 2, the value is 1. If x is 3, 3 squared is 8. The value of the output is 1/2. If x is 4, 4 squared is 16. The value of the output is 1/4. So let's see. We started with 4. We went down to 2. Whoops, we went to 1, didn't we? Okay, so let me find where my eraser is here. Okay. We then said, what was the next one? Erica, you've been giving these to me. 1/2, and then 1/4, okay. Well, let's jump a little bit, because we're trying to get to infinity. So what if x is 100? Let's see, 100 squared, isn't that 10,000? So if the input is 100, the output is how much? 4 10,000s? See, tens, hundreds, thousands, 10,000s? Okay. Well, what if the input is 1 million?
Or just keep approaching 0.
Absolutely. Why is that? Well, what's happening to the denominator? It keeps getting larger and larger and larger. How significant is the 4 as I let x go to infinity? Not very. Yeah, not very important. And so as the denominator gets larger and larger and larger, the numerator becomes almost, well, you don't even have to count it. And you get down to where it approaches 0. Would it matter if I made this to be 100 or 400 or 1,000? It's still going to, the denominator is going to far exceed the numerator, no matter what size, what value that is. Okay, so this is what it's saying, that if you have the input raised to a positive rational, now you say, well, you used a whole number, okay. Well, what if I let x be, let's say, 4 divided by x to the 1/10 power? Then what's it going to be? Let's see, if I put 1 in there, I'm still going to have 4, excuse me, if I put 1 in there, I'm still going to have 4 come out. If I put, 1/10 power, now I'm going to get myself in trouble again, aren't I? Do you know your 1/10 power table? Okay, so, okay, once again, let's just make it something we can relate to. How about 1/2? So now if I put 4 in there, let's see, the square root of 4 is 2, so that's 2, right? If I put 16 in there, the square root of 16 is 4, so that's 1. If I put 100 in there, the square root of 100 is 10, so that's 4 tenths. If I put 1,000,000 in there, what's still going to happen? It's still going to bring it down to 0. Okay, so that's what this theorem is saying. Intuitively, as the denominator is changing, but that numerator is not, then you're going to have a progression towards 0. Okay. Would it matter if I let the input go, to negative infinity instead of positive infinity? So let's go back up to this one. This began as, what was it, 4? If I have 4 divided by x squared, would it matter if I had it going to negative infinity. X is now negative 4, X is negative 16, X is, yeah, it won't make any, because you're squaring it. What if it was cubing it? Ah, that's different, isn't it? If I cube this, then if I have X to the negative 2, then that's negative 8, so that's 4 divided by negative 8. That'd be negative 1/2 and negative 1/4. Well, yeah, some of those would be negatives. If I cube, well, if I'm going to negative infinity, they're all going to be negatives, aren't they, as I go down there? So is it going to make any difference? No. And the only difference is that instead of going to 0 from the greater than 0 sign, I'm going to approach it from the less than 0 side. Okay, so we have this. Now the other one is that if we have e to the x power, this is taking a constant to an exponent. If I take e to the, get larger and larger and larger and larger values. Well, now let's look at this. This is, you got to look at this carefully. It's e to the x, where x is going to negative infinity, which is equivalent to saying that this is the limit as x goes to infinity of 1 divided by e to the x. If you have negative exponents, you take it across the fraction line. Okay. Once again, we're going to have a denominator far exceed the numerator, which is going to create a 0. Okay. Well, here we go. Limits again. Again, I think you've had some work with some of these algebra things we're going to be doing, but let's take a look at this. Intuitively, let's take a look at it. So we'll do a little intuitive aspect first. If I'm going to take the input to infinity, what part of the numerator becomes insignificant? The constant. What about the denominator? Same, yeah, the same thing. So we could say that this is equivalent to, or it's kind of the same thing as, the limit as x goes to infinity of negative 2x to the 3/2 divided by 3x squared. Now, if I have this fraction instead of the one I started with, I could say it's the limit as x goes to infinity. And let's see, I get a negative 2/3, and I subtract in the denominator, so I have negative 2x to the 1/2 power, which is equivalent to what? Well, here's that situation where we have our denominator varying, and as I increase the value of the input, what happens to its relative value to the numerator? And it's going to go to 0. Okay, that's an intuitive look. That's not the analytical one. That's just an intuitive look at this. But if we can think about it intuitively, then we're close to being able to reason out why our answers are correct or incorrect. Now, let's look at it in a more analytical way. If I have the limit as x approaches infinity, I'll put those in parentheses. What can I multiply? What can I multiply by that won't change the value of the original fraction? Very simply, it has to have a value of what? 1. Okay? What's that 1 going to look like? What if we made it 1 divided by x squared and 1 divided by x squared? Then I would have the limit as x goes to infinity let's see, this would be 5 divided by x squared minus 2 divided by x to the 1/2 divided by 3 minus 4 divided by x squared. What would be the advantage of looking at it in that way?